Lecture 39 of Physics 72 extends the discussion of reflection to surfaces, but this time we're looking at the formation of images from spherical or curved surfaces. This can be seen in subchapter 34.2 of University Physics. The objectives for this lecture are mostly like the previous lectures, but we will focus on spherical surfaces or spherical mirrors instead of flat mirrors. Because the surface will be a bit more complex than the last, we have an additional objective in determining where the image will form and what type of image will be formed based on a new concept called ray tracing. There are a lot of applications where we want the images formed to be larger or smaller. Magnifying glasses form images that are larger than the object, and surveillance mirrors shrink the images so that they cover more ground. In instances where we want the images to have different sizes compared to the objects, we use curved surfaces. Let's consider a curved surface that is easy to study for now, or spherical mirrors. Spherical mirrors have a property called the radius of curvature, which we define to be r, and this indicates how the mirror is shaped or how much of it is curved. Larger r indicates a flatter looking surface, and the smaller r indicates a curvier surface. R is infinity for flat surfaces. The picture on the left shows a convex mirror. It forcibly diverges the outgoing rays and has a radius of curvature that is less than 0. The mirror on the right is a concave mirror. It forces the outgoing rays to converge and has a radius of curvature that is greater than 0. One of the most common curved mirrors are seen in the kitchen, or spoons. Depending on which side of the mirror you look, the spoon can either act as a concave or a convex mirror. Notice how the different images will form. So these images will also vary depending on how far away you are from the spoon. Well, first we're going to look at its front side. So for our first case, let's consider the concave mirror. We look at the front side of the spoon. Before I continue, I'd like to emphasize that this video, or this lecture, won't really focus on the derivations of the equations that we will use in image formation. A relatively easy calculation may be found in the book. We'll focus on the intuition on some of the quantities that we're supposed to determine or that we're going to need to determine image location and magnification for curved mirrors. One such quantity is the focal length. To make sense of what this is, let's consider the figure on the right. From the lecture on ray propagation, we know that light rays will propagate radially from point sources. Now, these rays will start to look like they're parallel to each other when the source is very far away. So an example of well, not really a point source, but then a source that radially emits light waves, but then it's so far away that it will seem like the light rays are already parallel, is the sun. So the sun is very far away, and then when the light rays hit Earth, we can usually approximate that the light rays will be parallel when they strike the surface. So we consider such rays to be hitting a concave mirror, such as in the diagram on the right. After reflecting off the surface, there will be one point at which all of these light rays will meet. So after they hit the surface, all of them will eventually hit one point. So think of the magnifying glass targeting the rays of the sun, which is very far away from you, to a specific point that you want to, let's say, burn or heat up. This location is aptly named the focal point, or letter F, as you can see in the diagram here. Now, it looks like the rays are coming from the focal point, but then you have to realize that light rays are reversible. So you can imagine, instead of the parallel rays going outside of the mirror, they're going to approach the mirror. And either way, those are valid light ray diagrams for our concave mirror. Approximations with geometry dictate that this focal point is located between the mirror's center of curvature, or C, and the mirror itself. So this F is basically your focal point. The focal length is exactly half of the radius of curvature. We take both F and R to always be greater than 0, at least for concave mirrors. So we'll see later that image distances are dictated by this focal length. So the relationship between distance s and s prime are somewhat connected to this focal length of the concave mirror. And this relationship with object distance is given by the equation 1 over s plus 1 over s prime is equal to 1 over f. While we can locate the image by the equation I just said, there is a visual or a graphical way to determine the locations of images. That is, assuming that we keep the drawings legible and to scale. We call this method ray tracing. So it's a bit of a complicated diagram, but we'll go through it one by one. So consider a point object for now. And point objects will emit light rays from a single point. So it makes sense that this image will be located where these rays will meet at a single point again. Or replication is basically key. How are we supposed to find the next convergence of the points or of the light rays using ray diagrams? So sorry, this figure that we show is actually an extended object, but then as you can see at this point P, all of the light rays will originate, or at least the relevant ones. And then at this point Q prime, after hitting the mirror, these light rays will converge again. And this is where we will determine the image to be, because the light will be focused at this point. So, generally, there are countless rays coming out of the object. We only need to choose a few. And remember that rays are supposed to make electromagnetic wave representations easier. In fact, we only need to draw 2 particular rays out of the 4 that's shown here right now. We can choose these from a selection, which we call principal rays. Now, principal rays are connected in some way to the optic axis, that's number 4, the radius of curvature, number 3, or the focal point, 1 and 2. So let's go through them one by one. The first two, 1 and 2, are related to the focal point of the mirror. Remember that outgoing rays that pass through the focal point come from incoming rays that are parallel to the optic axis. This is our first principal ray, and it's the purple one. For the second ray, we can do a reverse of the incoming-outgoing process from the first example. We choose the incoming ray, so that's the green ray. We choose the incoming ray to pass through the focal point. And its outgoing ray will be parallel to the optic axis. We can do this because the direction at which light rays point the photon paths are reversible. The third ray passes through the center of curvature. But since radii are always perpendicular to the tangent lines of circles, so if I can draw an example here, the third ray is the orange one. Since it's going to pass through the center of curvature, I know that it's going to strike the mirror perpendicularly. So I can just expect the outgoing ray to actually go back the same path as the incoming ray. So this is our third principal ray, sorry. And finally, the last ray is not as, well, it can still be used, but it's not as used compared to the first three. It uses the optic ray, also optical ray. The optical ray would be this one, the long one here. And it uses the optic ray as an angle bisector, which easily shows the incident and reflected angles being equal from the law of reflection. So this would be the pink one, and since it's an angle bisector, we know that the incoming and outgoing angles are the same. To determine where the image will form, we choose two of these principal rays by drawing their starting point at the point object, or at point Q, and then we want to see where their outgoing rays intersect, which is point Q prime. This is the graphical method of determining image locations. And the only assumption that we have to make so far is that the mirror should be somewhat perfect or free of imperfections or aberrations. So let's see whether our ray diagrams and the equation for distances are consistent with each other. Consider a point object on the optical axis, point P. Object distance S will be positive, as what you usually set at the start, and R and F will always be positive. Now, one ray, not really the principal ray, will point to the image location, or the light blue one will eventually point to where the image will form. So, for the equation to make sense, S prime has to be positive. Seeing if our convention for image distances checks out, we see that our outgoing ray will be on the same side as the incoming ray. The image formed, or since the image formed will be on the left side, the rays will converge on the left for a concave mirror. If I draw, let's say, another wave, looks like this, I can expect it to hit that part because again, well, it will be confirmed later that you only need two rays to really determine where the image will form. So since the image form will be on the left side, the S prime should be positive as well. So the point object or the image for the point object should check out. But then we're not really concerned so much with the point object, but rather with extended objects. So that's the more interesting case. It's more interesting to study extended objects because we can also observe differences in object height and confirm its consistency with the equation of magnification. We're going to see later that unlike the flat mirror examples where the magnification is 1, or its absolute value is going to be 1, for curved surfaces it can actually change. It can be greater than 1, it can be less than 1, it can actually be negative. If it's negative, it means the object orientation is inverted. So for our first example, we're going to determine where the image is and how it's oriented by drawing the principal rays. The first ray uses the optical axis as the angle bisector, and the second ray passes through the center of curvature. The intersection tells us where the image is, as well as its height. And this is assuming that the rays are drawn to scale. Notice that y prime, or the image height, is less than 0, because the tip of the image would be below the axis. But if you look at it, the tip of the object is above the optical axis. From concave mirror conventions, we know that S prime has to be greater than 0. This is because the outgoing rays will always converge at the same side, well, where the image will form. No sight lines needed. Going back to the equation for magnification, we know that m will be less than 0 regardless whether we use the ratio of heights or distances. Well, as you can see, again, assuming that this is drawn to scale, the image is shorter than the object. For now, we know that it's less than 0 because the image formed is inverted. So if you use the y prime over y, it's a negative number over a positive number. And then since we know that s prime and s are both positive, using the other equation for distances has the negative sign. So m really has to be negative. So one way to verify this is we look at the front side of the mirror, or its concave side, and we have to make sure that we're going to look far away. Notice that the object is, or the object distance is larger than c. That's usually, or larger than f. So that's usually an indication whether the object will be inverted or not, whether it's real or virtual. So if your face is far away, the image will be inverted, similar to how the rays are drawn in this figure. So let's try to answer a quick exercise. A mosquito landed 20 centimeters in front of a concave mirror with a 20 centimeter radius of curvature, or r equals 20 cm. How far from the mirror will the mosquito's image be formed? So, we don't really necessarily have to use ray tracing for now. We can just use the equation that relates the object and image distances to the focal length of the mirror. Basically, we're going to be using 1 over s plus 1 over s prime is equal to 1 over f. The mosquito's location is S, which is 20 cm. Since the radius of curvature is also 20 cm, the focal length should be 10 cm. So if we're going to rewrite the equation, it's going to be 1 over 20 plus 1 over s prime is equal to 1 over 10. And then quick algebra, okay, 1 over s prime, if you isolate this part, it's going to be 1 over 20 as well. So that tells you that s prime, well, for 1 is positive, and it's located 20 cm to the left. So for this example, we're going to see, well, the mosquito inverted, but then at the same location as the well, as the object. So what it's going to look like is, if this is the mirror, and let's say that this is the object, the image formed will look something like this after you draw the two rays. Now that we have a basic idea of how concave mirrors generate images, let's check how convex mirrors do so. An example of said mirror will be the backside, or the bulging side of a spoon. Some of the conventions for convex mirrors are different compared to the concave mirrors. For one, focal length would still be half the value of r, but both f and r would take on values less than 0. We can reason that their values are less than 0 because the center of curvature and the focal point are located behind the mirror, or opposite where the outgoing rays are supposed to be. So unlike the concave mirror, the convex mirror will basically have F and C behind it instead of in front of it. Remember that the focal point is the point at which the light rays will converge. But then, if you look at it, it's going to be problematic if the light rays or the parallel light rays will be coming from the left. Because what a convex mirror does, from its other name, a diverging mirror, basically spreads out the outgoing rays instead of converging them. So how do we make sense of the focal point? Before we get to that, the equation regarding the distances and the focal length is exactly the same for the convex mirror. But then we have to take note that f will have a negative value. Now, convex mirrors diverge the outgoing rays, as I said a while ago. This means that there's no hope for them to converge on the right side, or actually on the left side. But then what we can do, as what we did with flat mirrors, we can extend their sight lines or the dashed lines on the opposite side or the right side. And if we do so, we see that the outgoing rays of parallel incoming rays will converge at the focal point through their sight lines. So this can only mean that the image formed by these convex mirrors are always virtual. The principal rays used for convex mirrors will mostly be the same, with a few added things to note when drawing them. Remember that the sight lines will converge, not the outgoing rays, so we need to extend the outgoing rays towards the other side. Now, the first ray, the reflected parallel ray, will appear to come from the focal point. So that's the purple one. So the incoming ray is parallel, the outgoing ray will extend out, but then if you draw the sight line, it's eventually going to touch the focal point. The second one, the incoming ray approaching the focal point, so this would be the green one. Notice that its incoming ray is focused towards the focal point, but then it will have an outgoing ray that bounces parallel to the optical axis. For the third one, the ray that approaches the center of curvature will hit the mirror perpendicularly, similar to the concave mirrors, and will bounce back the same way it approached. And finally, the light ray that gets reflected symmetrically and basically bisected by the optical axis is a possible principal ray. Looking at how a point object forms an image with convex mirrors, let's start with one ray. The sight lines, extended from the back of its outgoing ray, will indicate where the image will be formed. Now, since the image formed will not be on the same side as the outgoing rays, the image distance is negative, or s prime is less than 0. This is consistent with the fact that the sight lines will converge and not the outgoing rays, so from our indications with virtual images. The equation for distances and radius of curvature will still be the same compared to the concave mirror, but in this time, s prime and r will always be negative. As with our example with concave mirrors, extended objects give us an idea on how objects are magnified by convex mirrors. The first two rays, will be the one approaching from the center of curvature, and the second one is the one that uses the optical axis as the angle bisector. Drawing the sight lines shows the intersection, and this tells us where the image will form and how it's oriented. The images formed by convex mirrors will always be upright and virtual. This is not the case for concave mirrors. The front end of the spoon can form upright and inverted images depending on how far you are from it. So considering the conventions, we will always have a positive magnification for convex mirrors, but not necessarily greater than 1. So let's end this lecture with a quick exercise. And notice that it is very similar to the previous example with the exception that we have a convex mirror. Okay, so notice the values are the same. But now we're dealing with a convex mirror. This means that the focal length has to be f equals to -10. And if we use the equation 1 over s, so it's 1 over 20, it's still 20, plus 1 over s prime is equal to -1 over 10. We'll eventually get, we'll get 1 over s, sorry for the lag. Then this becomes -3 over 20, because, and then that tells us that s prime is 20 over 3, -20 over 3. We're going to draw the diagram. We consider that, okay, is this one. I can expect that the image formed, extend it this way, will be somewhat closer and shorter, but still upright. So this is it for lecture 39. Thank you for listening.